Let's do another problem, but this time we'll spin the graph about the y-axis instead of the x-axis. And it works just as well. When the symmetry is the right type of symmetry, it's an easier way to do a volume calculation. We're going to find the volume of a solid obtained by rotating the region bounded by y equals x to the third power, y equals 1, and x equals 0, spinning that y equals x cubed about the y-axis. So first, we're going to do step 1, find the points of intersection, and that gives us, well, we start by setting y equal to y. Set y equal to y and solve for x. So y, the first y, it's equal to x cubed. So we set x cubed equal to the other y, which is 1. Solving that for x, we get x equals 1 because we took the cube root. That gives us the ordered pair 1, 1. When x is equal to 1, y is equal to 1. How do we find y? Let me just remind you. When you want to find y, you just take the x that you just found, x equals 1, and you plug it back into either of the two y equations, either y equals x cubed or y equals 1. It's going to give you the same y partner. So that's how we got the y partner to x equals 1. Step 2, we're going to find the sketch of this thing. Now, I'm going to first show you what I'm going to get at the end after I spin it, and then I'll show you the the two-dimensional sketch. This is a three-dimensional idea here. Here's my y equals x. Oh, it's x cubed or x squared? Y equals x squared or x cubed? It's cubed. It's y equals x cubed, but this is what it's going to look like after we spin it around. Now you're probably thinking, but that looks like a parabola. No, it's actually not a parabola. It's part of the graph y equals x cubed up to y equals 1. And then it's going to be spun around the y-axis, okay? So C, the lower limit of integration, will be y equals 0, and D, the upper limit of integration, will be y equal 1. Now I'm going to cut out a little disk. This time it's a horizontal disk. And I'm going to pull that piece out and think about what it means to have that little disk. When we integrate, we're going to integrate over all the little disks glued together from y equals 0 to y up to y equal 1. Okay, so let's see what this picture looks like in 2 dimensions. Here is the line y equals 1, and here is the graph of just a portion of the graph of y equals x cubed. I'm only interested in the first quadrant again. That is y equals x cubed in the first quadrant. The whole graph would look like a snake, but we only need the first quadrant. Here's a little slice that I took out of my approximating rectangle. It has width delta y, and then here's the line x equals 0. We got our line y equals 1, and the curve is y equals x cubed. Now solve that for x, you get the cube root of y. Okay, so, and this is spinning. We're going to take this thing and spin it around the y-axis. And when we stack all these disks as we spin it around, we're going to get a solid that looks like the sketch above in 3 dimensions. It's going to be a solid, looks sort of like half of an egg. Step 3, we're going to find the area of the arbitrary horizontal face formed when we spin the estimating rectangle around the y-axis. It gives us a face of a disk that looks like this, with a point in the center and then a radius x. And so that means that's actually x equals the cube root of y. So the area as a function of y is pi times the radius squared, where the radius is x. So pi times, well, x is equal to the cube root of y. We solved for x and saw that it is equal to the cube root of y. So we replace x squared with y to the 1/3 squared. We get pi times y to the 2/3. Step 4, the volume of the solid of revolution is formed by taking the integral. That's the process of stacking these disks. After you've spun it around, you're going to stack the disk from the bottom at y equal the lower limit 0 to y equal 1. of the area of the face. And the area we found in step 3 is pi times y to the 2/3 power. So that's the integral of pi y to the 2/3 dy, which is equal to pi times 3/5 times y to the 5/3, evaluated from 0 to 1. Do the evaluation. I pulled out the constants, 3 pi over 5, and I evaluated y to the 5/3 at 1 minus the evaluation at 0. My final volume is 3 pi over 5 units cubed. So in this problem, you see we spun about the y-axis instead of the x-axis. So we took a horizontal disk instead of a vertical disk. And when we take a horizontal disk, we consider limits of integration of y values from c to d, and we also use a differential dy. So just compare this to the previous example where we were doing a similar thing, but we were doing it spinning around the x-axis.